First of all, I'd like to just say I work for the government, and if I say anything politically correct, I want to apologize in advance to Mr. Zubrin. But I am working on a non-politically correct project, but it is gaining more political backing, I think. I am really excited about the Mars Curiosity Rover. It has a nuclear power reactor on it. It did not have any protests when it launched. There was no protest. So anyways, with Fukushima and all that, there are people who are against that. We even heard about somebody breaking into Y-12 a couple of days ago as a protest. But nuclear power is becoming a little bit more in line with people's thinking, and nuclear thermal propulsion is essential for us to get back to Mars, or get to Mars with humans. Okay, first of all, I want to say I work under the Advanced Exploration Systems Program. A newly project that's been created under that is a Nuclear Cryogenic Propulsion Stage project. This is technology work to advance nuclear thermal rockets and the fuel elements that we can advance this technology so we'll be ready if the political, social, economic situations improve. So we're advancing this technology so we'll be ready if those things line up. Okay, well, first of all, why nuclear thermal propulsion? Nuclear thermal propulsion is a fundamentally new capability that was developed back in the 60s. We've invested close to $1.5 billion in those year money to advance this technology, and we've developed systems and rockets that have proven a capability that is 2 times better than any theoretical chemical propulsion. The only thing we haven't done is put it up in space and shoot it. And this energy comes from fission, not chemical reaction. By the way, the Mars Curiosity Rover had more radioactive material on the launch pad than any thermal rocket will have on the ground. The fission products that are produced are only produced at the point when the engine is started in orbit, heading away from the Earth. So it's fairly a benign system until we start the rocket. It's got virtually unlimited energy density. You could hold the amount of energy that's needed to go to Mars in your hand. Unfortunately, to create the creative or critical reactivity, you need a lot more. And unfortunately, because of that, right now with the state of it, the weight is quite significant, more than chemical rockets. Initial systems will have a specific impulse roughly twice that of the best chemical system. And we're talking about the beginning. As we work on this technology, as we use these rockets, we'll be able to increase that specific impulse even more. The chemical SSME, they were able to improve over time a little bit of specific impulse to increase the performance, maybe 3 to 5 seconds. We're talking about hundreds of seconds in the advanced ones. But let me get to the fuel element so that I can hand this over to Stan. Okay, I will be talking about other aspects of the other parts of the nuclear cryogenic propulsion stage, but today I want to focus in on the fuel design and fabrication work. Objective is to optimize advanced manufacturing processes to develop the nuclear thermal propulsion fuel material. We have a team that is comprised of Marshall and Glenn, and we have JSC involved as well, and KSC is starting to get involved too. We have DOE, Department of Energy, who will be helping us with a reactor. We have INL, ORNL, and LANL, although I need to update this chart. We're trying to recapture the Rover Nerva fuel element work, and that's one of the main things I'm talking about. We're fabricating the Serment, graphite composite, advanced carbide fuel element samples, and we're using depleted uranium. Anytime we actually use highly enriched uranium, there's a level of security involved and a lot more cost. And so right now we're developing the capability to even use the depleted uranium, and also we're using surrogates for testing as well. complete mechanical and thermal property testing to develop an understanding of the process, property structures as we run these fuel elements through the environment that it will see in the rocket. We just want to be able to quantify and qualify these fuel elements so that we can predict how long that they will be able to last in the thermal environment, thermal hydraulic environment, and be able to predict how well it will perform. Okay, as I mentioned before, is there a laser pointer up here? That's okay. Here we go. All right, the first two, the graphite and the composite, those were done back in the 60s and well qualified. We're trying to relearn that process. Some of the things that were used then isn't available now, but we want to develop those capabilities. Like the binder for the fuel element, nobody makes those anymore. We'll have to find another to be able to make that. Serments were worked on, although less technology, but as you can see, these fuel elements can endure higher temperatures, and you can see that as the temperature goes up, you have a greater capability of specific impulse. And we're currently targeting around 900 seconds. That will give us plenty of capability to send much more payload to Mars faster. Okay, fuel materials development. As I mentioned before, we're working on graphite composites, Sermets, using the hot isostatic process of putting those together, pulsed electric current sintering, and then we want to work on the advanced carbides. Those are even more advanced materials that will be able to run at higher temperatures. And there's no chemical process here. It's just a heating up of the material or the propellant that is expelled out of the engine, and that's what creates thrust. And the higher the temperature, the higher the ISP. We'll develop and characterize these consolidated samples, and we'll try to optimize, but that is not the main goal. The goal is to have something that works. And we'll do hot hydrogen testing. We have test environments that we will be able to put these fuel elements in and be able to test these fuel elements. Okay, part of fabricating these fuel elements is getting the components to put together. And the UO2 particle procurement, we've procured some amount of depleted uranium, and we have been certified to handle that. We want to be able to control the size of it, and we're developing processes to make them and control them to a certain spherical size. And we have the plasma spheroid system, which basically tries to melt the uranium and re-solidify it into spherical sizes at the appropriate sizes that we want. We also want to be able to coat these uranium particles. One of the main things that we have to do is protect the fuel, the uranium itself. And the best way to do that is to coat them in with tungsten is one material and be able to control that process. So we use the chemical vapor deposition process to make these spherical fuel sub-elements. Serment, we've chosen a form that the Argonne National Lab has developed, and I mentioned those two processes before. And then recent Serment work fabrication capability, we're actually building these right now, and testing them in the environments that they will see in a nuclear reactor, nuclear thermal rocket. Okay. And then there's the advanced carbides development, and this is a little bit more advanced work. And as you can see, it's more of a development plan phase right now, and we want to be able to quantify its capabilities and material properties. Here we have a coupon fuel element environmental test system. It'll be able to take these fuel elements that we build and put them inductively heat these elements and be able to heat them to the conditions of a nuclear thermal rocket, and then we'll be able to see how how it reacted in that environment. Did it break apart? Did it lose some of the uranium in the process? So we'll be able to test these. And the Oak Ridge National Lab fuel element work, they are focusing in on the Rover Nerva fuel, and this is the fuel mixture we are focusing in on. They made it work. Back in the 60s and early 70s, they made this work, and it was not due to any accident. They worked a lot of tests, and a lot of work went into it. So it doesn't make any sense to ignore what worked in the past. And we're trying to replicate it. Like I mentioned before, there's processes as well as materials that aren't available now that they used. And to be honest, we don't have a lot of good documentation of how it was done, so we have to figure this out. But anyways, we're building the same configuration, and ultimately we'll be able to test a fuel element assembly that you see over there that's from the Rover Nerva fuel work. We'll be able to test that at Marshall. Okay, with that, let me turn it over to Stan. He'll talk about the rocket that will use these fuel elements to take us to where we want to go. And I want to say this one thing before I turn this over. It's people like Stan Gunn, people like Mr. Zubrin who have the passion and who really do want something to happen and that work hard to change people's minds or give people a vision. It's my privilege to work with some of those people at NASA, as well as DOE. There are people like that. And when we work on these technology programs, they come up when NASA is transitioning from big projects like Shuttle and Constellation to something else. Technology work does get funding. Unfortunately, when those other big projects come up, technology funding dwindles, unfortunately. Okay.
I do. Put that on there.
Yeah. You can put that in your belt.
Okay. Is this everything I need? Okay. Want to take yours? You ready? Okay. I'd like to make the presentation now on what we did accomplish way back in the late 1950s to the very early 1970s in the way of fully developing the nuclear rocket propulsion system so it could be used in transporting the men to Mars and starting that program way back then. It was a program that was completed. Next slide, please. This is a summary of the tests that were conducted back in that period of time. And actually, the Los Alamos program is in green, and the Westinghouse Aerojet program is in red. From this chart, you can see that there were some 13 reactor configurations that we ran and tested as part of the Rover program, and there was a total of 6 different reactor or engine systems that were tested as part of the NERVA program. Next slide, please. This is a picture of the actual propulsion capabilities that we were targeting our development work on to be able to undertake the Man-Mars mission in one configuration, that is a 35-inch diameter core for the propulsion of the space vehicle. We also had the capability of reducing that down to something in the range of 15 to 25,000 pounds of thrust using a 20-inch diameter core, or going clear up to over 4,000 pounds of thrust, actually to 5,000 pounds of thrust, if we used the proven 55-inch core. So that was the capability that had been demonstrated. Next chart, please. This particular chart gives the performance that we were working with and the performance that we achieved, and for an expansion ratio of 500 to 1, which I'll get into more detail in just a moment, we could get an ISP of around 4860 temperature, an ISP of better than 920 seconds. Next chart, please. This is a diagram of the two configurations that we were focused on. The one that we selected was configuration B, in which the total flow coming out of the pumps, in this case we were going to use duplex pumps, went down first to two areas. One, the main flow was up through the cooled portion of the nozzle, which is down on the lower right-hand side, then on up to where this flow then joined the flow that was coming down, going through from the turbine exhaust, so that we ended up with a topping cycle where all of the propellant then ended up going down through the core and was available to get the full ISP. Next chart, please. Here is a picture or a drawing of the actual reactor system that we used. It was involving the fuel elements, which were clustered together in a group of 6, about a tie tube assembly, and then a cluster of 325 of those made up the entire core. Outside of that was the reflector, and in the reflector were the drums that were used to control the power level being developed. I'd like to make one point here, that as in a minute I'll get to it, that the existence of the internal shield with the later development was totally unnecessary. We didn't need any shielding on the engine, and we didn't need any shielding on the propellant tanks. The only shielding necessary was for the crew that was in the payload. Next chart, please. In terms of designing the final expansion ratio, which is an uncooled carbon-carbon composite thrust chamber, it started out at a thrust of around 150 to 1, area ratio around 150 to 1, and then went out to 500 to 1. And the benefits we got from that was a reduction in the wall temperature of that uncooled structure down to something in the order of around 2,000 degrees. Next chart, please. Well, this is a diagram of the variation of the parameters that were involved in the engine, and they varied all over the map, as you can see, but we could design and make it operate to all the parameters over that range. Next chart, please. This is a picture of the selected nozzle assembly for the 100,000 pound thrust version. It had a cool structure that came out of the surrounding flow coming down around the outside of the chamber, then went down into the converging section of the nozzle in a flowing system involving the tubular, rather the construction of coolant channels within the walls of the system. But then where you see the other portions, those are all tubular portions that went down to the 151 arbitrarily selected value. Next chart, please. This chart shows what could happen. This is a dual pump setup. What could happen if one pump happened to drop out or develop a problem and had to be shut down as to the change in the operating conditions and the thrust. The design point here is shown up there, the design point, and if there was that failure of one of the two pumps, the flow could drop to 50% flow and drop down the total thrust, but not take the whole operating area of the engine system out of action, just to reduce its intensity. Next chart, please. Here is a picture of the pump, turbo pump, that was developed for these series. This is an axial flow design in which there are 5 axial stations and the inducer stage with the overhanging turbine drive shown to the left there. In this particular case, and in the other cases we examined, it was found that the configuration shown could be engineered in such a way that it was always smaller in size, lighter in weight, and higher in efficiency than using centrifugal pumps. And the numbers there go that the change in efficiency is from 62%, which is typical of centrifugal pumps, clear up to 90 or 82% and higher with the pumps shown. Another important thing is the design improvements we put into that inducer on the far side. And that inducer, we made a change in the design of how the head was added to the fluid coming through, such that if there had been a case of development where the pressurization of the run tank containing the hydrogen was lost, this inducer still allowed the unit to run at full conditions, clear up to 30% of the total flow that was asked for. In other words, we could suffer that kind of a problem and still get the total mission done with that configuration. Next slide, please. The time after shutdown is of interest in knowing what we had to contend with in the way of heat generation after that point. And this particular chart shows that from a time period of 1/10 of an hour or 1/100th of an hour on out, there would be decay in the power coming down, and the thrust of the engine system you'd have to acknowledge in your planning of the mission as to how you were going to work with that. Next slide, please. Here's just simply some views of the various components that were designed for use in this engine, and the point being that we had the knowledge at that time to be able to make the units that are indicated above here, and they would function properly. This was not trying to get into something we didn't know anything about. This is something that was already been proven. Next slide, please. Here is the overall, on this particular size, 100K engine, view of the engine system, and we have an overall weight there of 18,000 pounds. It could have been reduced down if we'd have thrown away that uncooled portion of the nozzle, but the ISP would drop a little bit. So this shows the overall configuration and the conditions from the conditions where the tank is mounted to the engine as to where that's located. Next slide, please. Here's bring it up just a little bit, please. Well, maybe we can't get it all on there. That shows the parameters of the engine and its operation from all the way up to the main operating condition and then down and out. And this configuration represents something that we knew we could build at that point in time. And if the government had decided that they were going to go forward with manned missions to Mars, that engine could be created with the knowledge that we'd already demonstrated. Next slide, please. I think this is the final chart. Is there anything else I can do?
Do you want to take a few questions?
I'm happy to answer any questions that can be given. Thank you very much. Thank you. Come back there. Something, question?
Yes, I'd like to compliment you on your slide. Look at you, two people.
What was he saying?
He's impressed with the picture. Yeah.
Oh, yes.
What happens with the hardware? Does it still extend from the hardware that you guys actually created?
Some of it still exists, but what doesn't exist could be refabricated in short order. In other words, if a decision that we want to go forward with a program now, we could certainly be getting ready for it. We think, get the proper approvals, within 15 to 18 years, we'd be ready for launches. But that could be started right now. Yes?
Sir, when you say some of the materials don't exist currently that you used to use, what are those materials that we don't currently have?
Well, I was thinking then about the materials used in the reactor assembly itself. It's a question of what you want to get your hands on again to make the overall fuel elements. The other materials just plain exist. can be gotten, yes. Thorium? Oh, we didn't use that particularly. Maybe we should have, but we didn't. What we did was to take what we get our hands on, and it worked. We could sit there and watch it go. Yes, sir.
Which specific actions do you recommend that us space enthusiasts and taxpayers take to help advance a resurgence of fission-based propulsion systems? What can we do to help?
I'm not sure I heard you correctly. My hearing is not what it used to be.
My question is, which actions do you recommend that space enthusiasts such as us can take to help bring about, assist the resurgence in fission-based propulsion systems?
We could get that.
What can we do to help?
We could get that going as soon as people want to, with the people, with the organizations that exist, and still have the capability to make the parts that I was talking about. We could start now.
As individuals, it's difficult, but lobbying as a group can definitely help through organizations such as this.
Yes, sir.
Had you considered a partnership with the GSA?
Global position. Huh? Well,
They got endless amount of money. So
I see. Well, I don't know if there's any real problem with partnership, because if just a retrieval of what we got in the way of knowledge, and we could, people that want to work on it, we could do it now, not have to learn to teach them how. That's my point.
Yeah, actually, going back to that one question about being able to encourage fission, nuclear thermal power in space, there's myths out there, like the fact that, oh, this is a very dangerous system, it's going to kill people, or it costs a lot to develop. And there's numbers out there that people, without a lot of knowledge, say, okay, it's going to cost too much. Well, it shouldn't cost any more than a regular engine development. But there is a lot of fear there, so we have to educate people on the fact that it shouldn't cost any more. And we should be able to do this safely.
Yes, sir.
Is the test ban a factor in research?
The test stand itself, or location of it?
The test ban treaty, the nuclear test treaty, he's asking, is that a problem for nuclear thermal rockets?
I don't think so.
It shouldn't be,
It shouldn't be.
because we're not exploding. We're controlling it.
Now, as far as location of the development of this propulsion system, there are several locations that are possible. It's possible to take the exhaust gases that are coming out of the nozzle when any firing, and then to cool it off, and after you cool them down to one point, you can separate out the uranium materials or radioactive materials that are in that exhaust, as you would in a power plant, and then take it down the rest of the way. And this means that you don't have to go to a sophisticated underground system to do this. You can do it all above ground. And one place that I happened to go by to see was the one at Las Cruces, New Mexico, which is being currently used now by NASA. There's space there to put the necessary additional equipment there and do all of your testing there before you go into the launches.
One more question.
Yes, sir.
So obviously the main benefit of nuclear thermal propulsion is the mass savings, but you can get similar mass savings from mining your chemical propellant in space.
What would you say?
Well, you can get some amount, but even then, you're talking about less propellant needed with a nuclear thermal rocket compared to a chemical rocket.
By a factor,
Okay.
a big difference.
Yeah, it's just, right now, if you look at what a same mission would take for us to go to Mars, with launch vehicles costing $1 billion a piece. The nuclear thermal rocket could potentially save us 3 to 4 launches of a total of 10 launches for one of those big missions that Mr. Zubrin doesn't like.
If you don't get your propellant mass from space, if you get your propellant mass from space, then you save roughly 80% of your launch mass.
But you're still saving a lot with the ISP, whether it's any propellant with the nuclear thermal rocket.
With NTR, we could do Mars Direct with one launch instead of two.
Okay.
All right, we have to cut it off here. Thank you very much.
You bet. Thank you. Thanks very much.
Just a few words here. Okay, we're now going to have a 1-hour lunch break, after which we're going to reconvene with the multiple track sessions in the various rooms. These tracks have to be kept on schedule, half-hour talk. The first person to speak in the track is the provisional track chairman. Should stay there and keep people to a half-hour as required. If that person has to leave, the second person in the track should take over as track chairman. But you have to rigorously enforce this time. Otherwise, people simply won't get their chance to speak. So take your lunch break. See you back at 1. Thanks.